October 18th, 1944. Hindenburgstrasse, Aachen, Germany. The M12 sits behind a pile of rubble. 100 yards away stands the State Theater, 4 stories of reinforced concrete, walls 5 feet thick. Inside, 60 German soldiers, machine gun nests at every window. The building is a fortress. The gun crew has spent 2 hours trying to crack it. 75mm tank shells bounce off the concrete like pebbles. 105mm howitzers chip the surface. Nothing penetrates. The loader slides a shell into the breach. It looks ordinary, 95 pounds of olive drab steel. But screwed into its nose is a device that will change everything. A steel plug no bigger than a coffee can. The T-105 Fuze. The gunner sights the barrel. 300 yards, point-blank range. The gun roars. The shell hits the theater wall at 2,800 feet per second. Most shells would explode on impact. A burst of fire on the surface, smoke, maybe some cracks. This one disappears into the concrete. For 0.05 of a second, nothing happens. Then the building erupts from inside. The entire upper floor collapses. Steel reinforcing bars twist like wire. Concrete chunks the size of cars crash into the street. When the smoke clears, there's a hole in the building you could drive a truck through. The German commander will later file a protest. Using such a weapon at close range, he writes, is barbarous, should be outlawed. The Americans have a different name for it, door knocker. Fall of 1944. The Western Front has reached Germany's border. The Siegfried Line stretches 390 miles, from Holland to Switzerland. 18,000 bunkers, Dragon's Teeth tank traps, minefields. The Germans built it in the late 30s when they thought France might attack. Now it's the only thing standing between the Allies and the Ruhr. The bunkers are the problem. Type 10 fortifications, the backbone of the line. Walls 4 feet 11 inches thick. Ceilings the same. Reinforced concrete with steel rebar every 6 inches. Stepped embrasures for machine guns. Gas-proof. Heated. Built to withstand anything the French could throw at them in 1938. American artillery has gotten significantly better since 1938, but the concrete hasn't gotten any weaker. First Army has been hammering the line since September. 105mm howitzers, 155mm guns, even 8-inch artillery, high explosive shells that can level a house. Against these bunkers, they're making dents, chips, cracks that spider web across the surface. The concrete holds. Engineers try every trick they know. Bangalore torpedoes jammed into firing ports. Satchel charges against the doors. Flamethrowers. Tanks at point-blank range. A Sherman can pump 30 rounds of 75mm shells into a bunker and barely scratch the paint. The problem isn't the explosive power. American shells pack plenty of punch. It's where they're exploding. On the surface, a high explosive shell hits concrete and detonates instantly. The blast spreads out, not in. It's like trying to break a wall by slapping it. Hard. To break concrete, you need to get inside it, then explode. That requires 2 things. A shell tough enough to punch through without shattering, and a fuse that waits. First Army needs both. Fast. The Siegfried Line is costing them 300 men a day. At Aberdeen Proving Ground in Maryland, ordnance engineers have been working on this problem since 1943, testing shells against concrete slabs, 7 feet thick, German specifications. They've tried armor-piercing rounds, the M112, 100 pounds of hardened steel. Penetrates fine, but the explosive filler is tiny, 1.44 pounds, makes a neat hole, doesn't break the wall. They've tried heavier charges. The shell cracks on impact. They're looking for something different, not a new shell. They want to turn the shells they already have, regular high-explosive rounds with 15 pounds of TNT, into concrete killers. The solution, when they find it, is almost insulting in its simplicity. Change the nose. Aberdeen Proving Ground, Harford County, Maryland. August 1943. The Ballistic Research Laboratory has built a test range that looks like a piece of the Siegfried Line. Concrete slabs 5 feet thick, 7 feet thick, reinforced with steel rebar. Same specifications as German bunkers, same concrete mix, 4,200 pounds per square inch compressive strength. Captain James Morrison walks the line of targets. His team has been firing at concrete for 6 months. The results are piled behind the slabs, shattered shells, fragments, failed experiments. The Army has a problem. Actually, 2 problems that connect. Problem 1, armor-piercing shells penetrate concrete fine, but don't break it. They drill neat holes, make the bunker drafty, don't kill anyone inside. Problem 2, high-explosive shells break concrete great, but can't penetrate. They explode on the surface. Impressive fireworks. Surface damage. Morrison's job is to combine both qualities, make a shell that penetrates like armor-piercing and explodes like high-explosive, without designing an entirely new shell. They don't have time. They don't have factories. They have 17 million rounds of high-explosive ammunition already made and shipped. They need to modify what exists. The breakthrough comes from studying shell behavior in slow motion. High-speed cameras show that standard impact fuses function in about 0.003 of a second. The shell hits. The nose plunger compresses. The firing pin strikes the primer. The booster detonates the main charge. Total elapsed time, 0.003 seconds. At typical impact velocity, 2,800 feet per second, the shell travels about 8 inches in that time. For punching through thin walls, perfect. For thick concrete, not enough. The shell needs to be completely inside the concrete before it explodes. Morrison's team does the math. To penetrate 5 feet of reinforced concrete, a shell needs to remain intact for roughly 0.05 seconds after impact, 17 times longer than standard fuses. Creating that delay is the easy part. The M48 fuse already has delay elements, small pyrotechnic charges that burn at controlled rates. A simple modification can extend the delay. The hard part is the nose. Standard fuses have brass or aluminum bodies designed for thin-walled explosive shells. They're basically sophisticated light switches, sensitive, delicate, precise. Hit concrete at Mach 2 and they crumple like tinfoil. The shell body breaks. Game over. Morrison needs a fuse nose that's as hard as the shell body itself. Steel, heat-treated, strong enough to punch through reinforced concrete without deforming. WD 4140 steel, molybdenum alloy. Heat-treated to Brunel hardness 300 to 340. Roughly the hardness of armor plate. Machine it into a nose plug that screws directly into standard shell threads. Cavity inside for the delay element assembly. Modified booster below that. Total weight, maybe 10 pounds. The beauty of the design is what it doesn't change. The shell body, unchanged. The explosive filler, unchanged. The propellant charges, unchanged. The guns, unchanged. Only the nose is different. A crew can swap from regular fuse to concrete-piercing fuse in 30 seconds. Screw off one, screw on the other. The Ordnance Department designates it Fuse, Nose, Concrete Piercing, T105. October 1943. First live fire test. They use a 155mm high explosive shell. M101, weight 95 pounds. Explosive filler, 15 pounds TNT. Normally fused with a standard impact fuse for instant detonation. Today it wears a T105. Target, concrete slab, 5 feet thick, reinforced, vertical. The gun fires. The shell hits at roughly 2,800 feet per second. It doesn't bounce. It doesn't shatter. It disappears into the concrete. 0.05 of a second pass. The slab erupts from inside. A cone of destruction expands outward from the impact point. Concrete chunks the size of basketballs. Steel rebar twisted into corkscrews. A crater 2 feet deep, 3 feet across. They fire again. Same result. Again. The slab starts to look like Swiss cheese. By the end of the test series, they've achieved something remarkable. One round of 155mm high explosive with T105 fuse will penetrate completely through 5 feet of reinforced concrete. 2 rounds in the same impact area will demolish a 7-foot wall. The Army orders 100,000 T105 fuses. Priority production. They start shipping to Europe in February 1944. Each fuse comes with instructions. Can be used with any caliber from 75mm to 240mm. Interchangeable with standard contour fuses. For fixed rounds, assemble at ordnance depots. For separated ammunition, crews can install them in the field. The technical manual includes one critical instruction. Impact velocity must exceed 2,000 feet per second for reliable penetration. Below that, the shell might stop inside the concrete without fully penetrating. Delayed fuse fires anyway. Result, shell explodes while partially embedded, makes a crater, doesn't break through. Translation? Get close. The farther you shoot, the more the shell slows down. For guaranteed penetration of 5-foot walls, maximum range is about 2,000 yards. For 7-foot walls, get within 1,000 yards. For best results, get within 300. That's danger close. German infantry with Panzerfausts can hit you from 300 yards. Machine guns, mortars. Nobody said bunker busting was safe. September 12, 1944. The 7 Corps reaches the German border near Röttgen. Ahead lies the Siegfried Line, the West Wall. 400 miles of fortifications built between 1936 and 1940. After France fell in 1940, the Germans stripped it, removed the guns, took the ammunition, used the steel doors for Atlantic wall bunkers, left the concrete to rot. Now they're back. August 24th, Hitler ordered the line reactivated. 20,000 laborers, most of them teenagers from the Reich Labor Service, scrambled to re-equip 3,471 bunkers. The result is chaos. Some bunkers have guns, some have ammunition. Most have neither. The steel doors are gone. Machine guns sit on improvised wooden mounts. Fire control systems don't work. Telephone lines were stripped for copper in 1941. Doesn't matter. The concrete is still there. Type 10 bunkers, the standard design. Central shelter room for 10 to 12 men. Combat section 50 centimeters higher with embrasures front and sides. Each position is built into terrain for interlocking fire. You can't see one bunker without being in the field of fire of 2 others. Advance toward one. Get shot from the flanks. Try to bypass. The trail is pre-registered by artillery. Attacking the Siegfried Line is like fighting quicksand that shoots back. The 1st Infantry Division, the big red one, hits the line near Aachen. Within 24 hours, they've learned 3 things. 1. Infantry can't take pillboxes. Machine gun fire from embrasures cuts down anyone who approaches. Bangalore torpedoes don't reach the firing ports. Grenades bounce off. Flamethrowers have to get within 20 yards. Suicide distance. 2. Tank fire doesn't work. 75mm shells from Shermans hit concrete and explode on contact. Makes impressive noise. Chips the surface. The concrete laughs. High-velocity rounds from M10 tank destroyers. Same result. The 90mm gun on new M36 tank destroyers shows promise. but there aren't enough of them. 3. Bunkers only fall when artillery cracks them open, but regular high-explosive shells take dozens of hits, sometimes hundreds. A single Type 10 bunker might absorb 50 rounds of 155mm fire before developing structural cracks. First Army doesn't have time for 50 rounds per bunker. The Siegfried Line has 18,000 bunkers. They need a better solution. Enter the M12 gun motor carriage, nickname Door Knocker. The M12 is an ugly beast. A World War I French 155mm gun, the cannon de 155mm GPF, mounted on an M3 Grant tank chassis. The gun is so big they had to move the engine forward to make room. Driver and commander sit up front in an armored compartment. Gun crew rides in back in an open-topped fighting space with armor thin enough that rifle bullets can penetrate. The Army built 100 of them in 1942 and 43, immediately declared them obsolete, put them in storage. They sat in depots gathering dust until February 1944, when someone realized the invasion of France might need serious artillery. 74 M12s were pulled from storage, overhauled, and shipped to Europe. They arrived in June as part of 7 field artillery battalions: the 557th, the 558th, the 987th, the 989th, the 9991st, all designated armored field artillery, meaning they could keep up with tank columns. The M12 was designed for indirect fire, counter-battery work, reach out 14 miles and drop shells on German artillery. Standard artillery tactics: safe, boring, effective. Then they hit the Siegfried Line and commanders started using them wrong. Direct fire, point the gun at the target, eyeball the range, pull the trigger. It works beautifully. The M12's 155mm gun fires a 100-pound shell at 2,800 feet per second. With standard high explosive, the M101 round with 15 pounds of TNT, it makes a satisfying boom. With a T105 concrete-piercing fuse, it becomes a bunker eraser. September 16, 1944. First recorded use in direct fire role. Near Bilchen, 6 kilometers southwest of Aachen. A battery of M12s engages a line of Type 10 bunkers at 1,500 yards. Each gun fires 21 rounds. They're not calling shots, not adjusting fire, just hammering. When they stop, 8 bunkers are smashed open, walls cracked, roofs collapsed, interiors gutted. Total time, 40 minutes. 168 rounds. The German defenders call it artillery terror. Unrestricted shelling of defensive positions. Technically legal under the Geneva Convention, but psychologically devastating. Sitting in a concrete box while 100-pound shells punch through 5 feet of reinforced walls and explode inside is an experience that breaks men. American tank crews start requesting M12 support. Got a bunker problem? Call for the door knocker. It becomes the standard solution. Infantry locates the pillbox, marks it with smoke. An M12 rolls up, sometimes within 300 yards, and starts punching holes. The nickname originates from Aachen. Troops watch an M12 systematically demolish fortified buildings. Someone comments that it knocks on doors the way a bill collector knocks. Loud, insistent, capable of breaking the door down if you don't answer. Door knocker sticks. Alternative nickname, King Kong, for the raw power of the gun. When an M12 fires at low elevation, the muzzle blast kicks up a storm of mud and dirt that looks like an explosion. The recoil, even with the spade dug in, rocks the entire vehicle backward. The first time crews see it, they think something broke. Nothing broke. That's just what happens when you fire a 100-pound shell at Mach 2.3. One battery claims to have destroyed more than 50 bunkers in 3 weeks. The 991st Armored Field Artillery Battalion keeps detailed records. Between September and November 1944, they engaged 217 bunkers in direct fire missions. Success rate: 83% complete destruction, 14% partially destroyed, walls cracked but still functional, 3% no effect, usually because they were shooting at decoys. The key is the T-105 fuse. Without it, even a 150mm shells just chip concrete. With it, the shells become surgical tools. One round, properly placed, opens a bunker like a can opener. 2 rounds in the same spot demolish it completely. German after-action reports mention the psychological effect. Quote, "American heavy artillery employed in direct fire against fortified positions produces instant demoralization of defenders. Men refuse to remain in bunkers subject to this bombardment. Casualties are heavy, structural damage severe." Translation: it works. October 2nd, 1944. The 1st Infantry Division begins the assault on Aachen, first German city on the invasion route, once the seat of Charlemagne's Holy Roman Empire. Population 165,000, most evacuated before the battle. What remains is 246 Volksgrenadier Division under Colonel Gerhard Wilk. Understrength, exhausted, determined. Aachen sits in a depression surrounded by hills, not a natural fortress, but the Siegfried Line runs through it, the Scharnhorst Line to the west, the heavier Schill Line to the east. The city itself is honeycomb of fortified buildings, air raid shelters converted to strong points, cellars reinforced with concrete, every major structure a potential bunker. The 1st Division's commander, Major General Clarence Hubner, gives Wilk an ultimatum: surrender or face destruction. Wilk refuses. Hitler's orders: hold Aachen to the last man. Every building, every street, every room. The Americans switch to Plan B: systematic destruction. The fighting method is brutal but effective. Divide into small assault teams, 1 tank or tank destroyer per platoon. Armor keeps buildings under fire until infantry makes the assault. When they hit resistance, and they always hit resistance, bring up the specialists. Demolition teams with satchel charges, flamethrower teams, engineers with pole charges for doors. When the strong point is too tough for infantry, call the M12. The State Theater on Hindenburgstrasse becomes the test case. 4-story building, reinforced concrete construction, walls 5 feet thick, windows bricked up and converted to firing ports, machine gun nests on every floor, 60 German soldiers inside under orders to hold until relieved. October 16th. The 26th Infantry Regiment tries to take it with tanks. They pump 75mm rounds into the facade. The concrete chips. The Germans shoot back with Panzerfausts. 1 Sherman gets hit, burns. The assault stalls. October 17th. They try 105mm howitzers, indirect fire, high explosive, 2 hours of bombardment. When it lifts, the building is still standing, machine guns still firing. October 18th. Someone requests the 155. Hindenburgstrasse, October 18th. Morning. The M12 designated for the mission is from Battery C, 991st Armored Field Artillery Battalion, serial number 93. Crew has painted a name on the gun shield, Adolph's Assassin. The vehicle commander is Staff Sergeant Robert Price, born in Ohio, enlisted in '42, trained at Fort Sill, the Army's artillery school. He's been with the 991st since France, scored his first bunker kill near St. Lo. Since then, he's knocked out 43 pillboxes. He's gotten good at it. The mission briefing is simple. Target is the State Theater. Range, 300 yards. Ammunition, M101 high explosive with T105 fuse. Load, 10 rounds. Fire until the building stops shooting back. The M12 moves up Wilhelmstrasse under covering fire from tanks on both flanks. Infantry has already cleared the first row of buildings to prevent Panzerfaust ambushes. Lesson learned the hard way in September. The vehicle slides into position behind a pile of rubble that used to be an apartment building. Good concealment. Clear line of sight down Hindenburgstrasse. Price studies the target through binoculars. The theater is massive. Pre-war construction. Concrete frame with brick facade, 4 stories plus basement. The front entrance is bricked over, windows sealed, machine gun embrasures visible on 2nd and 3rd floors, muzzle flashes from at least 6 positions, standard German defensive conversion. Turn the building into a pillbox, defenders on upper floors, ammunition in basement, exit routes through interior walls into adjacent buildings. If you assault from one direction, they shoot you from the sides. If you try to bypass, they shoot you in the back. The M12 solves this problem by not caring about tactics. It just shoots through walls. Price gives the order, load high explosive, T105 Fuze, aim center mass, 2nd floor, middle window. The loader lifts a shell from the ready rack, 95 pounds. Olive drab paint, yellow stenciling, He M101. The nose is different from standard shells, heavier, steel instead of brass. The T105 Fuze. He slides it into the breech. The loader behind him passes up a propellant charge, cloth bag full of nitrocellulose. Zone 7 charge, maximum velocity. The breech closes with a metallic clang. The gunner adjusts elevation. 300 yards, almost point blank for a gun designed to shoot 14 miles. The barrel is nearly horizontal, crosshairs on target. Fire. The gun roars. Muzzle blast creates a wall of pressure that shatters windows on both sides of the street. Smoke and dust explode forward. The recoil drives the spade 6 inches into the ground. The entire vehicle rocks backward. Downrange, the shell covers 300 yards in 1/3 of a second. Hits the theater wall at 2,800 feet per second. The hardened steel nose punches through brick facade, through 12 inches of concrete, through steel rebar. The shell keeps going. 5/100ths of a second after impact, the delay element in the T105 Fuze burns through. The firing pin strikes the primer. The booster detonates. 15 pounds of TNT explodes inside the concrete. The wall doesn't crack. It disintegrates. A cone of destruction expands outward from the impact point. Concrete chunks the size of cars. Steel rebar bent into shapes that shouldn't exist. Brick dust that fills the street like fog. When it clears, there's a hole in the 2nd floor large enough to drive a jeep through. Machine gun fire from that position stops, permanently. Price orders a 2nd round. Same aim point. Different floor, 3rd story this time. Fire. The process repeats. Shell punches through. Delay. Explosion from inside. Another section of wall collapses. 3rd round, 4th, 5th. They're not counting hits. They're demolishing the building systematically, floor by floor, section by section. Each round creates a new crater. The structural integrity fails. Floors collapse into the basement. Ceilings cave in. By the 10th round, the entire front half of the theater is rubble. The German garrison tries to evacuate through the rear exit. American infantry waiting on the flanks cut them down. 40 soldiers surrender. 20 are pulled from the rubble. The rest died when the floors collapsed. Total time, 12 minutes, 10 rounds, 1 building erased. Price's report notes, T105 Fuze functioned as advertised, complete penetration before detonation, structural collapse achieved, no return fire after 3rd round, target neutralized. The German commander of Aachen, Colonel Gerhard Wilk, is captured on October 21st when his command bunker is reduced by direct fire from an M12. After his surrender, he files a formal protest with the American command. The use of heavy artillery and direct fire at close range, he argues, is barbarous, violates the spirit if not the letter of the Geneva Convention, should be prohibited. He specifically mentions the State Theater, describes the carnage inside after the bombardment, soldiers buried alive when floors collapsed, men trapped in basement when ceiling caved in. Quote, "Such weapons employed at such short range against defended structures constitute excessive and cruel force." The American response is brief. Indirect quote from the commander of the 26th Infantry Regiment. "Colonel Wilkes' forces spent 3 days shooting at my men from fortified positions. When we brought up sufficient firepower to knock those positions down, he suddenly discovered concern for humanitarian warfare. His protest is noted and filed." Translation: "We're not stopping. The tactic spreads across First Army. Every division wants M12 support. The guns become bunker-busting specialists. They develop techniques, tactics, rules of engagement. Rule 1. Get close. Maximum effective range for T-105 Fuze penetration is 2,000 yards. Preferred range is under 500. Danger close range, 300 yards, is normal. When you're punching through 5 feet of concrete, you need impact velocity. Distance kills velocity. Rule 2. Shoot low. Aim for the base of the wall, not the top. Concrete is weaker near the ground, more compression stress from the weight above. A shell that penetrates low and explodes inside can collapse the entire structure. A shell that hits high just blows off the roof. Rule 3. Multiple hits. 1 shell makes a hole, 2 shells make a crater, 3 shells bring down the wall. Keep shooting until the bunker stops shooting back. Rule 4. Watch the fuse. The T-105 is reliable but not perfect. Roughly 3% fail to function, usually because impact velocity was too low. If a shell hits and doesn't explode, give it 5 minutes. Sometimes the delay element is just slow. If it still hasn't exploded after 5 minutes, it's a dud. Mark it. Keep firing. Deal with unexploded ordnance later. Rule 5. Indirect fire doesn't work. The T-105 needs high velocity to penetrate. Lobbing shells at high angles, standard artillery practice, reduces impact velocity below the threshold. Direct fire only. Point and shoot. The technique proves so effective that by November, First Army issues new doctrine. When facing fortified bunkers, standard procedure is suppress with infantry fire, call for armor support, mark target with smoke, bring up M12, fire until structure collapses. Average time from target identification to complete destruction, 20 minutes. Pre-T-105 Fuze, average time to reduce a bunker was 6 hours, sometimes days. The difference is simple. Before, shells exploded on the surface. Now they explode inside. The Germans adapt, sort of. They start building decoy bunkers, concrete shells with no interior, fake firing ports. The idea is to draw American fire onto positions that don't matter. Waste ammunition, waste time. It doesn't work well. American crews learn to spot decoys by watching for muzzle flashes. No flash means no garrison means no threat. Don't waste shells. The real bunkers reveal themselves by shooting. When they do, they become targets. German defenders learn to abandon bunkers as soon as heavy artillery appears. Standing orders: when 155mm direct fire begins, evacuate immediately. Don't wait for the second round. The first shell creates an exit route, a hole in the wall. Use it. Run. Smart tactic. Saves lives. Also means the bunker falls without a fight. By late October, the Siegfried Line near Aachen has become a cemetery of shattered concrete. Type 10 bunkers with walls caved in, ceilings collapsed, interiors gutted. Some bunkers have multiple impact craters, evidence of repeated hits. Others have single massive holes, where a lucky shot found a weak point. The 991st Armored Field Artillery Battalion alone claims 112 bunkers destroyed between September and November. Other M12 battalions report similar numbers. Conservative estimate, 500 bunkers knocked out by T-105 fused direct fire in 3 months. That's 500 strong points that would have cost hundreds of casualties to take with infantry assault. 500 positions that no longer block the advance. 500 fewer obstacles between First Army and the Rhine. The cost? Roughly 10,000 rounds of 150 mm ammunition with T-105 fuses. In raw numbers, 20 rounds per bunker. In practical terms, 10 million pounds of TNT delivered through 5 feet of concrete into the interiors of German fortifications. The Siegfried Line was built to stop armies. The T-105 fuse turns it into a speed bump. The effectiveness of the T-105 fuse comes down to physics, specifically the difference between external and internal detonation. When a shell explodes on the surface of concrete, the energy disperses. Blast wave expands in all directions, up, sideways, back toward the gun. Only a fraction of the energy actually pushes into the concrete. Most of it wastes itself heating the air and making noise. The concrete absorbs some energy, creates cracks, spalls the surface, but the structure remains intact. You need dozens of hits in the same spot to accumulate enough damage to break through. When a shell explodes inside concrete, the energy has nowhere to go except into the surrounding material. The concrete itself becomes the containment vessel. Blast pressure builds up faster than the concrete can fracture. Result, explosive force does maximum work on the structure. The concrete doesn't just crack, it shatters. Fragments. The rebar reinforcement, designed to hold concrete together under tension, becomes a liability. The explosion tears the rebar out of the concrete matrix. What remains is rubble. The difference in effectiveness is roughly 15 to 1. One shell exploding inside does the damage of 15 shells exploding outside. The T-105 fuse makes this possible through precise delay timing. Too short, the shell explodes before fully penetrating. Too long, the shell passes completely through and explodes on the far side. Sweet spot, 0.05 seconds. 50 milliseconds, long enough for the shell to bury itself 3 feet into 5-foot concrete, short enough that it detonates before punching out the back. Ordnance engineers at Aberdeen calibrated this delay through extensive testing. They built concrete slabs with embedded pressure sensors, fired shells at different velocities, measured penetration depth over time. The results showed that at 2,800 feet per second impact velocity, a 155 mm shell travels approximately 3.5 feet into reinforced concrete before momentum bleeds off. Add 0.05 seconds delay, shell is fully embedded when the fuse functions. The physics of penetration involves 3 factors: shell mass, impact velocity, and nose hardness. Mass matters because kinetic energy equals 1/2 mass times velocity squared. A heavier shell carries more energy. 100 pounds at 2,800 feet per second delivers roughly 8 million foot-pounds of kinetic energy. That energy gets converted into penetration work, crushing concrete, pushing rebar aside, compressing the material ahead of the shell. Velocity matters more than mass because energy increases with the square of velocity. Double the speed, quadruple the energy. This is why impact velocity threshold is critical for T-105 effectiveness. Below 2,000 feet per second, penetration drops off exponentially. Below 1,500 feet per second, the shell might not penetrate at all, just creates a crater and bounces off. Nose hardness determines whether the shell survives impact. Concrete at 4,200 psi compressive strength is hard, harder than brass, harder than mild steel. Standard fuses crumple on impact. The shell body breaks. Explosive spills out. Nothing penetrates. The T-105's hardened steel nose, Brunel 320, is harder than the concrete. When they collide, concrete loses. Steel wins. Shell penetrates intact. The delay element inside the T-105 is a small pyrotechnic charge. Burns at controlled rate. Aberdeen engineers tested dozens of compositions before finding the right burn rate. Too fast, shell explodes prematurely. Too slow, shell passes through before detonation. Final design uses a modified M48 delay element, proven reliable, simple to manufacture. Burns consistently across temperature ranges from -40 to +120 degrees Fahrenheit. The booster, the component that translates the delay element's small explosion into the detonation of the main charge, required modification too. Standard M20 booster is too sensitive. Risk of premature detonation during shell's violent deceleration inside concrete. Modified version has reinforced housing, 3 inches of steel threads instead of 5, reduced sensitivity. Still functions reliably, but requires stronger input. The delay element provides exactly that. Assembly is straightforward. Steel nose plug threads into shell body where standard fuse normally goes. Delay element screws into cavity inside nose plug. Modified booster threads into shell body below delay element. Small explosive train runs from delay element to booster to main charge. When delay burns through, it fires the booster. Booster detonates the main charge. Total weight of modification, 10 pounds. Cost per fuse, approximately $12 in 1944 money. $12 to turn an ordinary high-explosive shell into a bunker killer. The return on investment is spectacular. By November 1944, the T-105 fuse is standard equipment for 1st Army artillery units. Every battalion has them. Every fire mission against fortifications specifies them. Supply lines bring them forward by the truckload. Production numbers tell the story. The Army ordered 100,000 T-105 fuses in February 1944. By September, half are delivered to Europe. By November, they're ordering another 100,000. By December, 200,000 total produced. Manufacturing ramps up at 3 facilities: Watervliet Arsenal in New York, Rock Island Arsenal in Illinois, and Picatinny Arsenal in New Jersey. Each facility machines the steel nose plugs from WD-4140 stock. Heat treatment brings hardness to specification. Threading cuts to match standard shell nose threads. Delay element assemblies manufactured separately, mostly at Frankfurt Arsenal in Philadelphia. Boosters modified from standard M20 production. The process is simple enough that field ordnance units start manufacturing them locally. Instructions in the technical manual include machine shop drawings, tolerances, material specifications. A unit with access to a lathe and heat treatment furnace can make T-105 fuses from scratch. Quality isn't as consistent as Arsenal production, but they function well enough. European Theater of Operations reports using T-105 fuses on every caliber from 75 mm to 240 mm. 81% of usage is 155 mm, the sweet spot between shell weight and gun availability. 150 Fadenay guns are everywhere. Long tom-towed artillery, M12 self-propelled guns, even M40 gun motor carriages, the upgraded M12 on M4A3 chassis that starts arriving in 45. Each fuse is reusable if recovered intact. Doesn't happen often. Most get destroyed in the explosion. But shells that fail to detonate can have the T-105 fuse removed, inspected, and reinstalled on a new shell. Field ordnance tries to recover duds when possible. The steel nose plugs alone are worth salvaging. $12 in manufacturing cost, 35 cents in raw materials if you can reuse the steel. Actual dud rate is lower than expected. Aberdeen's testing predicted 5% failure rate. Combat usage shows 3%. Most failures occur when impact velocity is too low, shells fired at extended range or high angle. When crews follow doctrine, direct fire under 2,000 yards, fuse reliability exceeds 97%. The Army classifies T-105 as a limited standard fuse, meaning it's good enough for war, but not quite good enough for peacetime arsenal production standards. Too many variables, too dependent on impact conditions, works brilliantly in its specific role, wouldn't trust it for general-purpose use. Nobody cares. The war is happening now. The Siegfried Line is made of concrete now. The T-105 breaks concrete now. Peacetime standards can wait. By war's end, estimated total production exceeds 350,000 T-105 fuses. Not all see combat use. Many remain in inventory when Germany surrenders. Post-war, most are destroyed. The design is too specialized. Limited peacetime application. Steel nose plugs are valuable enough to salvage, melted down for scrap. Delay elements and boosters go to demolition dumps. A few survive in museums, artillery collections, ordnance displays. They sit in glass cases next to standard impact fuses. Visitors walk past without noticing. Just another piece of old ammunition. Nothing special. The bunkers they destroyed don't exist anymore either. Most were demolished by German engineers during their own retreat, deny the Allies' use of fortifications. Others collapsed from battle damage. Some remain as ruins, crumbling concrete in French and German forests. You can still see the impact craters, holes where 155 mm shells punched through and exploded inside. The Siegfried Line lost to a steel nose and a 50-millisecond delay. German military engineering reports from late 1944 reveal awareness of American concrete-piercing tactics. Wehrmacht engineers studied captured T-105 fuses, conducted tests on damaged bunkers, issued warnings. From German 7th Army Report, November 1944. American artillery has demonstrated new capability against reinforced structures. High-explosive shells employ delayed-action fuses that penetrate concrete before detonation. Effect is devastating. Standard Type 10 fortifications offer no protection. Walls 5 feet thick are breached with 2 to 3 rounds. Interior damage severe. Casualties heavy. Garrison morale collapses rapidly under this bombardment. The report recommends countermeasures. Thicker concrete, 7 feet minimum instead of 5. Spaced armor, layers of concrete with air gaps to disrupt shell penetration, sloped walls to deflect incoming rounds. All excellent suggestions in theory, completely impractical in practice. Building thicker bunkers requires more concrete, more steel, more labor. Germany in late 1944 has none of these. Instead, they issue new defensive doctrine. From LXXXX in Corps Tactical Memorandum, December 1944. Fortified positions subject to direct fire from heavy American artillery are to be evacuated immediately upon first impact. Do not attempt to hold under sustained bombardment. Withdraw through prepared routes. Reoccupy position after bombardment ceases if structure remains intact. Translation: run when they start shooting. SS Obersturmbannführer Gerhard Wilk, former commander of Aachen Garrison, provides detailed testimony after capture. Quote, "The American use of heavy-caliber artillery in direct fire mode at close range represents the most effective counter to fortified positions encountered in this war. Standard concrete fortifications offer no defense. The psychological effect on defenders is immediate and complete. Men cannot remain in positions subjected to this fire. The knowledge that walls 5 feet thick provide no protection destroys will to resist." Wilk specifically describes the theater engagement. He was not present at the building during the attack. His command post was 3 blocks away, but he interviewed survivors afterward. Quote, "The garrison reported hearing the first shell penetrate the front wall, a distinct sequence, impact, sound of shell boring through concrete, then explosion from inside the structure. The entire front section collapsed within seconds. Survivors described the interior walls being pushed outward by pressure, floors falling, ceiling caving in. Those who escaped did so only because the shell impacts created exit routes through the walls. Those who remained in position were buried when the floors collapsed into the basement. 20 soldiers killed, 40 surrendered, 0 wounded evacuated. The survivors were the ones who ran fast enough. German engineers who examined the wreckage noted specific damage patterns. From 7th Army Engineering Section report, analysis of destroyed bunkers shows consistent effect. Shell penetration creates cylindrical cavity through wall. Detonation inside concrete produces radial fracture pattern. Primary cracks extend from detonation point in all directions. Secondary cracks form along lines of stress concentration, typically around rebar junctions. Spalling occurs on both entrance and exit faces. Net result is structural failure of the entire wall section. Reinforcing steel pulled out of concrete matrix. Wall strength reduced to 0. They calculated the explosive effectiveness ratio. One shell exploding inside concrete does roughly 14 times the damage of one shell exploding on the surface. Their numbers match American estimates almost exactly. The reports recommend that all bunker construction cease. Quote, "Expenditure of resources on fixed fortifications that can be breached with 3 rounds of heavy artillery represents inefficient allocation of materiel and labor. Recommend shifting defensive strategy to mobile operations, dispersed positions, and preparation of successive fallback lines rather than static bunker defense." High Command ignores the recommendation. Hitler's orders remain unchanged. Hold every position. Defend every bunker. No retreat. By January 1945, Wehrmacht engineers stop building new fortifications. They focus instead on demolition preparation, rigging intact bunkers with explosives so they can be destroyed during retreat rather than captured. The Siegfried Line, 18,000 bunkers built over 4 years at cost of billions of Reichsmarks, survives American assault for roughly 3 months. The T-105 Fuze costs $12.50 milliseconds. The math favors America. November 1944. The Hurtgen Forest. 20 square miles of dense woodland southeast of Aachen, part of the Siegfried Line's eastern defenses. The terrain is nightmare fuel. Steep ravines, mud trails, trees so thick you can't see 50 yards. The bunkers here are different, not the open ground Type 10s from the border. These are forest positions, camouflaged, dug into hillsides, built into ravines. The concrete is the same, 5 feet thick. The challenge is finding them. 7 Corps enters the Hurtgen in mid-September. Objective: cut through to the Roer River dams, 7 miles of forest. Should take a week. Takes 3 months. Costs 33,000 American casualties. The Germans call it the Blutmühle, the blood mill. The bunkers are part of why. You can't see them until you're right on top of them. Standard approach: infantry patrol advances through trees. Machine gun opens fire from camouflaged position 50 yards away. Patrol takes casualties, calls for support. Artillery can't help, can't see target through forest canopy. Air support can't help, same reason. Tanks can't help. Ground is too broken, too muddy, can't maneuver. Bringing up an M12 through Hurtgen is difficult. The tracks help. Ground clearance better than wheeled vehicles. But the gun is huge. Trees are close. Fire lanes don't exist. You can't shoot what you can't see. The solution is unglamorous. Engineers with chainsaws cut fire lanes, clear sight lines. When a bunker reveals itself, mark it. Bring up the M12. Shoot through the trees if necessary. The 155mm shell doesn't care about tree trunks. The 557th Field Artillery Battalion operates in Hurtgen from October through December. Their after-action report describes 27 bunker engagements. Quote, "Terrain severely restricts mobility and field of view. Most targets engaged at ranges under 500 yards due to forest density. Direct fire only. High explosive with T-105 Fuze standard ammunition. Average rounds per target, 8. Average time to target neutralization, 30 minutes including approach time. 8 rounds per bunker. More than open ground, because you can't see well enough to put every shell on target. But still vastly better than trying to take them with infantry. The report notes that forest positions collapse differently from open ground bunkers. Quote, bunkers constructed into hillsides exhibit different failure modes. Penetration through front wall, successful, but roof structure often remains intact due to earth overburden. Recommend multiple impacts at different points to ensure complete structural failure. Bunkers built into ravines particularly difficult. Restricted approach limits firing positions. They develop forest-specific tactics. Approach from upslope when possible. Shooting downward into bunker is easier than shooting upward. Clear trees in a 100-yard radius around firing position prevents ricochets off trunks. Mark target with tracer fire from infantry weapons so gunner knows where to aim. Fire 3-round salvos instead of single shots increases probability of hitting camouflaged target. The Germans adapt too. They start building decoy bunkers made of logs covered with concrete mortar. Looks like reinforced concrete from distance. Shell penetrates, hits hollow interior. Explodes. Looks like success. Real bunker 30 yards to the left opens fire while Americans celebrate. American crews learn to spot fakes by watching for secondary explosions. Real bunker, ammunition inside, explosion creates secondary blasts when stored munitions cook off. Fake bunker, nothing inside, just primary explosion. If you don't see secondaries, keep looking. The Hurtgen is where the T-105 proves it works in worst-case conditions. Dense forest, restricted visibility, close range, difficult terrain, still functions, still destroys bunkers, still saves lives. By December, when 7 Corps finally reaches the Roer River, they've neutralized an estimated 80 bunkers in the forest. Most fell to T-105 fused direct fire. The alternative would have been infantry assault. At Hurtgen's casualty rates, roughly 100 men per day, 80 bunker assaults might have cost 4,000 casualties. The T-105 didn't make Hurtgen easy. Nothing makes Hurtgen easy, but it made it survivable. The T-105 works so well that ordnance starts adapting it to other calibers. 75mm, 105mm, even 8-inch. Same principle. Different sizes. The 75mm version is the lightest, designed for M4 Sherman tanks. Weight, 14 pounds. Nose plug diameter, 3 inches. Delay, 0.04 seconds, slightly shorter because the lighter shell has less momentum. Penetration at 2,000 feet per second, 2 feet of reinforced concrete. Not spectacular, but better than standard rounds. Useful against fortified buildings and light bunkers. Combat testing shows mixed results. Quote from 3rd Armored Division Report, December 1944. 75mm T-105 Fuze functions as designed, but penetration insufficient for standard Siegfried Line bunkers. Effective against Type 5 and Type 7 positions, lighter constructions with walls under 3 feet thick. Against Type 10 bunkers, recommend using 150mm support. Translation: works on thin walls, doesn't work on thick ones. The 105mm version is the sweet spot for howitzers. M2A1 howitzer, standard divisional artillery. Weight, 33 pounds. Nose plug diameter, 4 inches. Delay, 0.045 seconds. Penetration, 3.5 feet. Good enough for most bunkers. Not quite as effective as 150mm, but close. Advantage, every division has 105 howitzers. Lots of them. 12 per battalion, 3 battalions per division, 36 tubes. If you can give them T-105 fuses, suddenly divisional artillery can engage fortifications effectively without calling for heavy artillery support. The disadvantage is range. 105mm howitzers are indirect fire weapons, designed to lob shells over hills, high-angle trajectories. The T-105 needs direct fire, low angle, high velocity. Using howitzers in direct fire mode is technically possible but tactically awkward. You're basically driving your artillery up to the front line and shooting at things you can see. Artillery crews don't like this. Artillery crews prefer being several miles behind friendly lines where German machine guns can't reach them. Some units try it anyway. The 29th Infantry Division uses 105 howitzers in direct fire during the assault on the Roer River dams. Report notes: 105 with T-105 effective against bunkers at ranges under 1,000 yards. Crew exposure to small arms fire significant. Recommend use only when heavier artillery unavailable or terrain prevents indirect fire methods. The 8-inch version is the monster. M1 8-inch howitzer. Separate loading ammunition, shell and propellant loaded separately. Weight, 240 pounds. Nose plug diameter, 7 inches. Delay, 0.06 seconds. Penetration, 7 feet plus. There's nothing on the Siegfried Line that can withstand 8-inch T-105. Reports from 1st Army Heavy Artillery battalions describe bunkers being vaporized. Quote, direct hit from 8-inch T-105 produces complete structural collapse. Target bunker ceased to exist as coherent structure. Reinforcing steel blown into fragments. Concrete pulverized. Effect comparable to demolition charges placed inside the bunker by combat engineers. The problem is availability. The Army has relatively few 8-inch howitzers, heavy, difficult to transport, slow to emplace. They're strategic weapons, corps-level assets. You don't get them unless you really need them. When you do get them, you tend to save them for important targets. Using an 8-inch gun to knock out a single bunker is like using a sledgehammer to swat a fly. Effective but wasteful. Still, when nothing else works, 8-inch T-105 is the answer. Fort Driant, near Metz, one of the Maginot Line's eastern forts, falls to 8-inch bombardment after resisting everything else Third Army could throw at it. Walls 12 feet thick, standard shells bounced off. 8-inch T-105 drilled through and exploded inside. Fort surrendered after 3 days of this treatment. All variants share the same basic design: hardened steel nose, delay element, modified booster. Only the dimensions change. Ordnance Department standardizes manufacturing. Same facilities produce multiple calibers. Watervliet Arsenal makes 75 and 105 millimeter. Rock Island makes 150 mm. Picatinny makes 8-inch. Supply chain delivers them to Europe in mixed lots, convoys carrying all calibers. By spring of 1945, estimated inventory in European theater exceeds 200,000 T-105 fuses across all calibers. Roughly 60% are 155 mm, 25% 105, 10% 75, 5% 8-inch and larger. Not all get used. Germany surrenders in May. Suddenly there are no bunkers left to destroy. Post-war, most T-105 fuses sit in depots waiting for a war that's already over. Some ship to the Pacific. Japan has bunkers too. Most just age in storage until they're declared surplus and scrapped. The design doesn't disappear. Post-war artillery development incorporates the lessons. Delayed fuses become standard for all armor-piercing and concrete-piercing munitions. The specific T-105 design is retired, replaced by more sophisticated electronic fuses with adjustable delays. But the principle remains. To break thick concrete, penetrate first, explode second. Wait 50 milliseconds. Changed artillery forever. Before T-105, typical bunker assault, September 1944. Example, Type 10 position near Rötgen. Infantry approaches under covering fire. Machine gun from bunker pins down the assault. Infantry calls for tank support. Sherman moves forward. Fires 75 mm high explosive at bunker. 30 rounds. Results: surface spalling, minor cracks, machine gun still firing. Commander calls for artillery. 105 mm howitzer battery engages from 2,000 yards. Indirect fire. 50 rounds. Results: exterior damage, embrasure partially blocked by rubble, bunker still functional. Commander escalates. Requests 155 mm fire. Long Tom battery engages. 75 rounds over 3 hours. Results: significant damage, roof cracked, wall fractured, garrison still holding. Engineer assault team approaches under smoke cover. Bangalore torpedoes aimed at embrasure. Explosion. Garrison returns fire. 2 engineers killed. Assault fails. Second engineer team with pole charges approaches from different angle. Places 20 pounds of TNT against bunker door. Detonates. Door damaged but not breached. Garrison still inside. Flamethrower team attempts to spray fire through damaged embrasure. Range insufficient. Can't get close enough without exposure to machine gun fire. Team withdraws. Final solution: siege. Artillery continues bombardment. Infantry surrounds position. Wait for garrison to run out of ammunition or water. Time elapsed: 6 hours. Rounds expended, approximately 200. Casualties: 8 killed, 14 wounded. Result: garrison eventually surrenders when ammunition runs out. After T-105, same scenario, November 1944. Infantry identifies bunker, marks position with smoke grenade. Commander requests M12 support. Gun moves into position, 400 yards from target. Direct line of sight. Gunner loads 155 mm HE with T-105 fuse. Aims, fires. Shell penetrates front wall. Detonates inside. Explosion visible through embrasures. Smoke pours from firing ports. Second round, same aim point. Another internal explosion. Front wall develops large crack. Third round, wall section collapses. Interior exposed. No return fire. Infantry approaches. Finds garrison dead or unconscious from blast overpressure. Structure uninhabitable. Mission complete. Time elapsed: 12 minutes. Rounds expended: 3. Casualties: 0. The difference is stark. Pre-T-105, bunker assault is costly, time-consuming, casualty-intensive. Post-T-105, it's a mechanical process. Identify, mark, shoot. Next target. Operational impact shows in the campaign timelines. First Army reaches the Siegfried Line on September 12th. With pre-T-105 tactics, penetrating the line takes until late November. 3 months. Estimated casualties: 30,000. With T-105 available in quantity by October, the rate of advance increases. Bunkers that would have required hours to reduce fall in minutes. Strong points that would have halted entire divisions for days become minor obstacles. By November, breakthrough is imminent. By December, First Army is across the Roer River, except where the Rötgen forest delays them. Post-war analysis by U.S. Army Operational Research Section estimates that T-105 Fuze reduced average time to neutralize fortified positions by factor of 12, reduced ammunition expenditure per target by factor of 8, reduced casualties by approximately 60%. Fewer infantry assaults means fewer men exposed to defensive fire. The German perspective appears in post-surrender interviews. From General der Infanterie Gustav von Zangen, commander of 15th Army. American artillery's ability to breach fortified positions with delayed action fuses represented qualitative advantage against which we had no effective counter. The Siegfried Line was designed to withstand attack by contemporary artillery using impact fuses. The American development of penetration fusing made our fortifications obsolete. We could not rebuild to thicker standards. We could not develop countermeasures. We could only evacuate positions under fire and concede the breakthrough. British military observers studying American tactics note the same effect. Quote from British 21st Army Group Intelligence Summary, December 1944. U.S. First Army employment of concrete-piercing fuses with heavy artillery has proven decisive in reducing Siegfried Line fortifications. British forces facing similar defenses in Holland have achieved less rapid progress using standard munitions. Recommend urgent production and supply of equivalent fusing for British artillery. The British start their own program. By February 1945, they're manufacturing copies of the T-105, designated Fuse, armor-piercing, concrete, number 57, functionally identical, used in 25-pounder and 5.5-inch artillery. Results match American experience. Bunkers fall faster, casualties drop. The lesson is simple. In modern war, fortifications are only as strong as the weapons attacking them. When those weapons evolve, fortifications become tombs. May 8, 1945. Germany surrenders. The Siegfried Line still stands. Sort of. Large sections remain intact, bunkers in remote areas that never saw combat. Others are ruins. Walls caved in, roofs collapsed, interiors gutted. Most bear the distinctive signature of T-105 fuses, neat circular entry holes with explosive damage radiating from inside. Post-war, the French and Germans demolish thousands of bunkers, blow them up with surplus ammunition, bury them under roads, use them as foundations for new construction. By 1950, most of the line is gone. Some remains. Nature conservationists preserve sections as historical monuments. The bunkers become biotopes, wildlife habitat. Small mammals nest in the ruins. Plants grow through the cracks. The concrete slowly weathers. You can still visit them. Tourist sites near Aachen, hiking trails through the Hurtgen. The bunkers sit in the woods, half buried by decades of leaf fall. Some have interpretive signs explaining their history. Most are just ruins. You can see the damage, impact craters where shells punched through, interior walls blown outward, the signature of internal detonation. The T-105 fuses are gone, scrapped after the war, steel melted down, delay elements destroyed. A few survive in museums, artillery collections, ordnance displays. They sit in glass cases next to other obsolete ammunition. Visitors don't notice them, just another old fuse. Nothing special. The men who used them are mostly gone too. The gun crews of the 557th, 558th, 987th, 989th, 991st Field Artillery Battalions. The M12 drivers and loaders and gunners. They came home in 1945, went back to farms and factories and offices, didn't talk much about the war. When they did, they talked about other things. Not about bunker busting, not about concrete-piercing fuses. Nobody remembers the T-105. It's too specific, too technical, not dramatic enough for stories. When people think about World War II artillery, They think about Normandy bombardments, Bastogne's Christmas shelling, big battles, famous guns. They don't think about a steel nose and a 50-millisecond delay. They don't think about how $12 worth of molybdenum steel changed the entire campaign against the Siegfried Line. But the bunkers remember, the ones still standing. You can read their story in the concrete, the circular holes, the internal damage, the way the walls failed from inside out. The T-105 wrote its name in shattered fortifications from Aachen to the Rhine. 200,000 fuses, 7 months of combat, thousands of bunkers destroyed. It never got famous. It just worked. And sometimes that's enough. October 18th, 1944. Hindenburgstrasse, Aachen. The M12 rolls back from the theater. The building is no longer a building. It's a pile of concrete chunks and twisted rebar. Smoke rises from the rubble. No machine gun fire. No resistance. Staff Sergeant Price climbs down from the gun. He's covered in concrete dust. His ears ring from the muzzle blast. He walks to the rubble pile, looks for survivors, finds none. The garrison died when the floors collapsed. He notices the entry holes, clean circles where shells punched through. Diameter matches 150 millimeters exactly. The concrete around the holes is fractured, radial cracks spreading like spiderwebs. Interior walls are blown outward. The fuses worked perfectly. Price has destroyed 44 bunkers since France. This is number 45. He'll destroy 23 more before the war ends. But this one matters. First major strongpoint in Aachen broken by direct fire. Proof that the tactic works. Proof that the T-105 does what Aberdeen claimed it would do. He doesn't know any of this. He's just a gun crew sergeant doing his job. Load, aim, fire, repeat. Move to next target. Simple. The war is full of simple things that add up to victory. A steel nose, 50 milliseconds, $12, 5 feet of concrete. One explodes before the other breaks. The other breaks before anyone escapes. The building that wouldn't fall, falls. The bunker that couldn't die, dies. The line that was built to stop armies becomes a memory and rubble. And the fuse that made it possible never gets famous. Just effective. Just another tool in the arsenal of democracy. Just the thing that turned fortifications into tombs and walls into dust. The Siegfried Line learned the hard way. The hard part about concrete isn't making it strong. It's keeping the explosions outside. When the explosions move inside, concrete becomes history. The T-105 moved them inside. History followed.